Alrighty, welcome back. This is lesson 4, I believe, on simplifying some of these algebraic expressions. So this is where this unit takes a little bit of a turn and switches gears a little bit and talks more about the variable side of things, solving equations, that sort of thing. So let's think about what happens with regular square roots first, like radicands that are numbers, things that you can actually take the roots of, and then we'll translate some of that understanding into variables. So if you think about some of the ones that you see on here, and again, all the links to these are going to be in that description box. You can print out a blank one if you want, or have the solutions nearby if you just try it on a sheet of paper. You can do that as well. So think about the left column here first. Okay, we'll kind of ignore the other ones. So if you take the square root of 36, remembering that we could have 6 as our principal root. That's what our calculator is going to tell us. Square root of 49, 7, 10. I can square root all of these. And then when you take the square root of x squared, remember that, well, x multiplies with x to give you x squared. So x is going to be that square root, right? You can have the same thing multiplied by itself to get you that radicand. Now the same sort of thing happens if you look at the cases on the right column here. Now, 6 squared is really the same thing as 36. So if you square root 6 squared, the square and the square root are going to cancel. They're opposite operations, so you end up with 6, 7, 10 again. But now this is x to the power of 4. Essentially, this cuts the exponent in half. So think about x to the power of 4 as being x squared times x squared. Again, the same thing multiplied by itself to give us our radicand, so our square root here, x squared. So you can think about this on the variables as us cutting the exponent in half. Okay, and there are some important things that come out of this. Now, when you're working with an algebraic expression, especially if it's got radicals, we need to make sure we state any restrictions. Okay, any restrictions on that radical. Sometimes you could have a variable underneath your root sign. If we don't know what it is, before we solve it, we should be able to determine what values it can't be. Especially if you think about square roots, we can't actually square root a negative number. So if our value for x that we find is negative, well, that causes a little bit of a problem because we can't actually evaluate it. So think about the square roots of all powers that have something that is an even exponent, right? X squared, x to the power of 4. Those square roots are defined for every value of x. So x can be any real number, right? Which makes sense. So think about doing something like the square root of x squared, right? So we'll think about this case for a second. So if x is negative 2, for example, right? X could really be anything. But if x is negative 2, that means we would take out x, put in negative 2 in its place, and remember that if x is being squared, negative 2 is what's being squared. The brackets are important, especially if you try this in a calculator. The negative should be inside your set of brackets. Right, there's x squared. If x is negative 2, well, that means when I square that, I get 4. And 4 is a number you can actually square root. So as long as your exponent is even, essentially what you're going to see is an even number of negative signs. Right? So if that's what we're squaring, we're really doing negative 2 times negative 2. The negative signs cancel out, and I'm just left with a positive. And that happens anytime the exponent on that variable is even. Now, on the opposite side of things, if it's odd, right? If I have an odd exponent instead, something like x to the power of 1, x cubed maybe, x to the power of 5, think about this one. Again, if we just pick a number for x like negative 2, well, x cubed would say negative 2 gets cubed, and that means it's negative 2 times itself 3 times, which will get you negative 8. And if you try to take the square root of negative 8, your calculator will tell you that there is an error. It can't be done here. Now, there's no number you can multiply by itself to get negative 8. It just doesn't work. So you can't ever take the square root of a negative. Okay, and you're going to know that you can't because you're going to have an odd exponent on your variable. There will always be a negative sign remaining. So when you think about the restriction here, well, this only works if x is already a positive number. So for example, 2 cubed, right, that will give me 8, positive 8, which I could cube root, or sorry, which I could square root, or if x is 0. But if x is a negative value, it does not work. Okay, I can't square root negatives. Okay, and the key here is the radicand must always be greater than 0. Right, whatever the expression is, if your radicand is negative, you can't square root it. Now, just keep in mind that over the last few videos together, we said that you can add or subtract like radicals when they have the same index and radicand. Okay, so we can still combine and simplify some things as long as we state what the variables can or can't be, right? There could be a restriction. And we can use various properties to help simplify this. So these 3 properties are going to help. Now the commutative property basically just says that multiplication can happen in any order. So a times b is the same thing as b times a. And if you need a numerical example, well, 2 times 3 is 6, which is the same thing as 3 times 2. You can flip them around, the order doesn't matter. Distributive property is something we've talked about. So you've got something on the outside of a set of brackets, which really means you can multiply inside, so a times b plus a times c. And again, if you want a numerical example, there's one. I can distribute the 2 inside to that set of brackets for 2x plus 4. The last one is kind of, it's one we've used before, especially when we rationalize the denominator, the multiplication identity. So essentially what it means is as long as you multiply by 1, you haven't changed anything, right? The value's the same. The only thing that changes is what something looks like. But that 1 can take on whatever form you need it to be, right? 1 could be the whole number 1, it could be 2 over 2, it could be root 4 over root 4, it could be x over x. It doesn't matter, all of those things represent 1. Multiplying by 1 changes nothing, is essentially what this says. So you can multiply by 1 and nothing happens. It just makes your expression look different, which may lead you to be able to simplify something you couldn't before. Okay? So let's think about, stating a restriction and then simplifying. So if you take a look at this, there are certain numbers which might cause a problem here for x. So think about our exponent on the x. Right? So think about our radicand. So I'll write it out. The radicand is what could potentially cause the problem. Here it's x to the power 6. Now that has an even exponent, which means if I put a negative in for x, the negatives will all disappear. I'm going to end up with 6 of them. They'll all cancel. So I'll end up with a positive every single time underneath that radicand, or underneath the root sign. Right? Your radicand will always be positive because of the even exponent of 6. So what that tells you is there's no restriction. Right? If I put in a negative value for x, for example, negative 2 to the power of 6 leaves me with positive 64. If I put in a positive number for x, I still get a positive number. So I'm just using a couple examples to test this. Negative number gives me a positive, positive number gives me a positive. If I put 0 in to the power of 6, I'm going to get 0, but I can square root 0 and it's totally fine. So there's no numbers, no sets of numbers that I could pick that don't work here. So there's no restriction. X could be literally anything you want. Now I just can't solve for it quite yet. I don't have enough information. There's no equal sign to make an equation. So I can't solve it, but I can simplify this. So think about how we've simplified things together in the past. Right, x to the power 6, well that's a perfect square because I can write x cubed times x cubed. So when you simplify this, well that's already a perfect square, so square root it. Essentially your exponent gets cut in half to 3. So there's your simplification, and our restriction would say that x is any real number, xer, right? X is a real number. or x belongs to the set of real numbers. Both mean the same thing, but it essentially means there's no restriction, right? It could be any real number you want. Any number, any fraction, any decimal, whatever. Okay, think about C. This one looks different, right? I'm adding something this time. And again, one of the key things we underlined up above, and I'll even scroll back for a second, it says that the radicand must always be greater than 0. It has to be, right? If it's a square root, your radicand cannot be negative. So think about x plus 3, right? That's our radicand. Let me actually write this out. So the radicand must be greater than 0. Right? It has to be. So in other words, you could say that x plus 3 has to be greater than 0, right, in terms of an inequality. Now we said that if it is 0, I could still square root it, so I could be greater than or equal to 0. That's still fine. But now I have to find the value of x that makes this possible. Right? X plus 3 can be greater than 0, which is fine, but that doesn't really help because there should be one number which will tell me everything I need to know. So think about getting rid of this 3 and moving it to the other side of your inequality, and which would tell you that as long as x is greater than or equal to -3, this will work. And if you want to see if that restriction actually works the way it should, you can do this using a little bit of a table. Okay, so we'll do this one together, and we'll have to think about 3 different cases of numbers. So think about maybe if x is equal to that -3 value. Think about a number that's bigger than -3. 0 is larger than -3. Think about a number smaller, like -4. Okay, so equal to, one bigger, one smaller. Okay, 3 different cases. Now if x is equal to -3, our original expression said the square root of x plus 3. So put in -3 for x, add 3 to it. This is where you see the square root of 0. Now I can actually square root it, so that's okay. That's fine. So if x is -3, we're still in a good place. I can get a value still. If x is a number larger than -3, well, we'll start the same way. We'll take our original expression. We'll just test this out, see what happens. Now I just chose these numbers based on personal preference. You can pick any number in the world. 200 is again another number larger than -3. But what you'll notice is you always will get to a place where you can square root something. Right? -3 is not a perfect square, but you can still square root it. But think about that -4 off on the other side. Right? Think about what happens if we put that in to our original expression. Right? -4 plus 3, we get to a place where -1 is underneath. And we said we can't square root negative numbers. That one doesn't work. So any number that's smaller than -3 will not work, which is why our restriction is actually the correct one. Right? If it's equal to -3, I can still get a number that will work. Right? I can still square root it. It's still all good. But if it's bigger than -3, it's still good. Right? So I don't really know what x is, but I know it has to be -3 or more. If it's something less than -3, I won't be able to take the square root of it. So I know my restriction's good. And we're not going to be able to simplify it based on what we know. Right? I don't have a way of really simplifying this. So we're just going to leave it just like that. Okay, our restriction is decided on. It's all set. I don't really want to do anything else to this. Okay. Think about B. I kind of went in a weird order. Again, we want our radicand to be greater than 0 or 0. Right? If it's those two things, we can actually square root it. Now it's x cubed, which says we have an odd exponent. And again, if the exponent's odd, we said if x is negative, we will end up with a negative value, which I can't square root. So again, this is a place where x needs to be greater than or equal to 0. I don't have to do the other method I did with the last one, because there's nothing being added or subtracted to this, right? It's really just this expression that we care about. So 0 goes in for x. You can take 0 and cube it, you get 0, so that's fine. Pick a number bigger than 0, like 1. 1 cubed is 1, you can do that. Pick a number less than 0, negative 1. Negative 1 cubed will be negative 1, and it won't work. Okay, we can simplify this one. If you remember, x cubed could be written as x squared times x, which is essentially what we did with numbers. Right? Factor it, write it as the product of a perfect square and something else. Take that perfect square to both factors you just came up with. The one that's the perfect square gets square rooted, and you put everything back together using multiplication. The steps we talked about are the same, they just have to do with variables now as well. It's the only change, really. Right? We still did a perfect square and something else, we still square rooted it. All things are the same, we just have to say our restriction. And here's where it actually matters. We simplified this a bit, and we're left with the square root of x. Right? I can't square root negative, so this really shows that x has to be 0 or more. Anything less than that won't work. Think about this one. You've got a fraction this time. X is in 2 places. Right? Again, if you look at your radicand, it's x to the power of 1 without really saying it, which is an odd exponent. So that means x needs to be greater than or equal to 0. But if you think about the denominator for a second, you know in math you can't ever divide by 0. We said our restriction was greater than or equal to 0. But if it's 0, this expression won't be able to be evaluated. So it can't be equal to 0 this time because of the denominator. So I can just take out that equal sign, and we can say it's strictly greater than 0. I can't be equal to it because as soon as I am, then I get to a place that says 0 divided by 0, and it's not a good thing for us to be able to do. Right? It really doesn't do what we think it does, and I can't divide by 0, so I can't be equal to it. Anything greater than 0 is excellent. And again, there's not much I can simplify. These aren't like radicals. I can't add or subtract. I can't divide because I don't have a root sign on the bottom. This is okay. We can leave it as is for all of our purposes. Okay, but there's my restriction. X has to be greater than 0. Okay, so I'll let you try A and B here. And again, the full answer key will be in that link in the description box. So try them out, see how they go. We'll talk about a couple of these here. Right, restrictions and then simplify. If you think about A, well, look at all the radicands. They're the same, right? So that's good. I only have to think about one restriction. And again, the exponent on the variable is 1. That's an odd exponent, which means x has to be greater than or equal to 0. There's your restriction. If you go to simplify them, they're already like radicals. So take a look at your coefficients and combine. 15 minus 7 is 8. Minus 1 more is 7. So 7 square root 2x with the restriction x is greater than or equal to 0. Okay, so all simplified, everything put together. Think about B underneath. 3x cubed looks like the radicand we care about. Again, it's a square root that we're working with. You can't square root negatives. The x has a cube attached to it. That's an odd exponent. X is greater than or equal to 0. Okay, think about combining your like terms. So 36 minus the 10, add 28. In total, you have 54 square root 3x cubes. But if you look at your radicand, we could actually simplify them a little bit more, right? X cubed has a perfect square factor in it. So we can do 3 times x squared times x. X squared is our perfect square factor. Square root it. It goes to the outside. So 54. When you square root x squared, you get x. You're left with a 3x on the inside. And there again is your restriction. X needs to be bigger than or equal to 0. If you look at that root sign, you've got x to the power 1. If it's negative, your whole radicand is negative, which you can't take the root of. So there's where we need our restriction. For D, again, you can look at those radic. Oh, I forgot about C. Let's go back up there. Take a look at your radicands again. They are x. That is x to the power of 1. X needs to be greater than or equal to 0. That is an odd exponent. But now I can multiply, right? So 10 square root x squared. And this is why we always do the restriction first, because if I just use the original expression, well, I have a restriction, right? X can't be negative. But as soon as you get to here, well, it's x squared. Now my exponent has changed, which I can actually square root to get 10x. So it looks like I don't have a restriction, but it should always be based off the original. Because if you don't simplify it, well, then you can't have negative. So it should always be based off the original expression. And we're going to say x can't be negative, right? So x is greater than or equal to 0. Simplified, everything is where it needs to be. Again, same restriction for this one. Greater than or equal to 0 because you've got a square root of x to the power of 1. And now this is our distributive property like we've talked about. So there's 1, there's 2, there's 3, and there's 4. The 4 places we're going to multiply. 5 times 5 is 25. Our purple one we'll do next for a positive 5 root x. In orange, a negative 5 root x. And in blue, a negative root x squared. Okay, we'll put everything together that we can, and what you'll notice is the middle ones will cancel. So you get 25 minus, well, x, because the square root of x squared is x. Your restriction's still there because we have to do it in the first step. So there it is, there's a restriction, and then we simplified. Okay. So there you have it. All the rules are still the same, except we have to determine what values cannot be square rooted in that specific example. All right, we'll talk about these two. I won't do the A and B at the bottom. I'll let you try those ones, and again I'll have the answers because they're very similar to what we just did. Example 3 here is more of that rationalizing piece we talked about in the last one, right? Getting rid of that root sign in the bottom. So we'll do these two. And again, this is where you want to multiply by that special 1, which is really the denominator here. So for us, we're going to think about doing a root 3 as our version of 1 to make our root sign on the bottom disappear. And then you can multiply like normal. So on the top, you're going to get a 2 root 6. On the bottom, a square root 9. And this is why this works out so nicely, because square root of 9 is 3. Again, you're going to see it in 3 places. 1, 2, 3. That number, 3 happens in 3 spots. But now you can't simplify this anymore, because 2 divided by 3 doesn't work. You can't do 6 divided by 3, because the 6 is under the root sign, the 3 is not. There's your final result. Okay, as simplified as you can make it. But if you think about B, well, now there's just 2 parts getting divided by that root 7. So this is still the same, and just multiply the top and the bottom by your root 7, right? There's your 1. But this time, you're going to have a root 7 multiplying with a 4 root 3 plus your root 2. So this is a distributive property example. And on the bottom, you get your square root 49. So when you distribute to the top, I'll use some colors here, orange and blue. If you do the blue one first, you're going to end up with a root 14. And then in orange, you'll have a plus 4 root 21. On the bottom, the square root of 49 is 7. And I don't think 14 has any perfect square factors in it, neither does 21, but our root sign's gone, which is what we wanted. So I can't really simplify anything else anywhere. We're done. Right? Like if you think about factoring 21, it's 7 times 3, 1 times 21. Like there's really nothing else that you can use, and none of those are perfect squares that will help. So right there is our simplified result with our root sign from the bottom gone. Okay, so again, I'll leave A and B so you can try the restrictions, and I'll have it ready for you in the link there. There's one lesson left in this unit, so that'll be our next video where we talk about actually solving the equations. Okay, what this allows us to now do. So look out for that video, and we'll see you in the next one.